Welcome to the Department of Toxic Substances Control workshop on motor vehicle tires containing zinc, priority product proposal. My name is Jessica Anderson, and I am the Public Participation Specialist with the Department of Toxic Substances Control, which we will refer to as DTSC throughout this session. I want to thank you for taking the time to join us today, especially during these challenging times. We sincerely wish you and your families well and are keeping safe. This workshop is scheduled for 9 a.m. to 12 p.m., and the purpose of today's webinar is to present information on why DTSC is considering listing motor vehicle tires containing zinc as a priority product and to hear your feedback. Michael Ernst and I will be facilitating today's workshop. Slide 2, please. You are in a view and listen only role. Today we'll be taking questions through the Q&A feature, so please click on the Q&A button at the toolbar at the bottom of your screen to send your questions or comments. You may send them at any point throughout the webinar, and we will respond during the Q&A sessions at the end of each presentation, followed by a full public comment and question and answer section at the end of the presentation. You may send as many questions as you want. However, we request that you send one question at a time so we are able to respond to them adequately. We will do our best to respond to the questions in the order that they are received, and any remaining questions will be answered at the end of the workshop. Please note that we will not be taking questions by chat function. And for those of you joining by phone, please press *9 to raise your hand to let us know you have a question. You will be called on and prompted to unmute yourself. We also encourage you to send your questions or comments to saferconsumerproducts@dtsc.ca.gov, and we will do our best to respond during the Q&A session. Lastly, please know that we're hosting this webinar from different locations, so we request that you bear with us if there's any lag time or other technical issues. We sincerely appreciate your patience, understanding, and cooperation in making this a successful meeting. Slide 3, please. The agenda for today's workshop is broken down into 2 parts, with a short Q&A after each presentation, followed by a public comments and remaining Q&A discussion. Part 1 will include the general intro and opening remarks. We'll have a DTSC presentation from Dr. Ann Cooper, and then we'll have presentations from the California Storm Water Quality Association and the U.S. Tire Manufacturers Association presentation, followed by a break for about 10 minutes. We'll rejoin at 10:30 from presentations from Dr. Kelly Moran from the San Francisco Estuaries Institute, Dr. Eric Van Genderen, and Dr. Adam Ryan from the International Zinc Association, Ken Schiff from the Southern California Water Research Project, and Dr. Ali Ansarifar from the Loughborough University. We'll finish with some public comments, as well as the Q&A and some closing comments. I will now invite Carl Palmer, Deputy Director of DTSC's Safer Consumer Products Program, to give us opening remarks, followed by Michael Ernst, Hazardous Substance Engineer, to begin our presentation. Carl?
Thank you, Jessica. Good morning, everyone. Thank you for joining us for this workshop. I'm really pleased to launch this workshop, and over the next day and a half, we'll have 2 additional workshops. This morning, we'll be talking about zinc. This afternoon, we'll be talking about other chemicals of concern in tires. And tomorrow, we'll be talking about 6-PPD in tires. And I hope you can join us for all 3 workshops. Today, I'm really pleased to welcome and thank our speakers today. We have the benefit and blessing of a lot of really super smart people who are working in this area. We have folks from stormwater agencies, we have researchers, we have academics, we have the tire manufacturers represented. And so we're going to have a lot of good information today. Before we kick into the program, I just want to, in addition to the thanks, I want to remind folks of a couple of things. One is the Safer Consumer Products Framework regulations are very different than most environmental and health regulations that we're used to dealing with. And it's important to note that this road that we're on, sorry for the metaphor, we don't predetermine where it ends up. What we predetermine is the desire and the mission to make products safer for people and the environment. We don't want to compromise safety. We don't want to have regrettable substitutes that come out of well-intentioned actions. And this is why we implemented regulations which have a robust alternatives analysis process, and it's an iterative process that we believe leads to good outcomes. So it takes some patience, and it's an iterative process. It's also a precautionary process. We know there are a lot of data gaps, but we also, our mission is not to wait around till we answer every question, but to take action with good information. And so thus the workshop today, you'll see some of the findings that we have, the learnings that we've experienced, and you'll hear from a lot of other smart folks about their information. But I want to encourage you to look at the documents that we posted online, the technical documents, to provide your input. We need as much information and expertise and wisdom as we can get so that everyone can make good decisions, DTSC, the manufacturers, and everyone along this road. So with that, I again thank you to all of our speakers. Thank you all for participating, and we'll look forward to today's workshop, and I hope you'll join us this afternoon and tomorrow as well. So with that, I'm going to turn it over to Michael to go from here. Thank you.
Thank you very much, Carl. Good morning, everyone. My name is Michael Ernst, and I'm a hazardous substances engineer with DTSC's Safer Consumer Products Program, also known as SCP. The purpose of this presentation is to give you a brief overview of the Safer Consumer Products petition process and explain why DTSC decided to grant the California Stormwater Quality Association's petition to list motor vehicle tires containing zinc as a priority product. Next slide. Oh, sorry, slide 4, please. And slide 5. The Safer Consumer Products Program uses a 4-phase process to reduce potentially harmful chemicals and products. As Carl said, this is a very iterative and deliberative process designed to encourage safer products while avoiding regrettable substitutes. We start our process with our candidate chemical list. This list is based on the work of other authoritative bodies and contains approximately 3,300 chemicals or chemical classes of concern, including zinc. The next step involves identifying products containing one or more of these chemicals that may cause harm to human health or the environment. Product chemical combinations determined to have the potential for harm are designated priority products. The identification and prioritization process is usually done by DTSC. However, our regulations also allow people to petition us to add or remove product chemical combinations from the priority product list. Now, when something is added to our priority product list, manufacturers are then required to conduct an alternative analysis. The goal of this analysis is to determine, 1, if the chemical of concern is necessary, and if so, 2, are there safer alternatives that can still meet the functional performance and safety requirements for the product? I'm sure that's no surprise to anyone joining us today that tires are heavily regulated to ensure consumer safety. And it's really important to point out that any potential alternative that comes from this process will have to meet the exact same safety standards as tires today. It is also entirely possible for the alternatives analysis to show that there are no safer alternatives at this time. In the final step of our process, DTSC uses the information from the alternatives analysis to issue a regulatory response. This is not always necessarily a product or chemical ban. Our regulations include a wide range of possible actions DTSC can take to protect human health or the environment. Other options, other potential options in this case could be requiring manufacturers to reduce the amount of zinc in tires, or potentially funding research and development of safer alternatives. It is also possible for DTSC to decide to take no action at all. Slide 6, please. On this slide, you see an overview of the petition process. Once a petition is submitted, DTSC first performs a completeness review to determine if it contains all the items specified by the regulations. Once DTSC determines that a petition is complete, we then begin a merits review to determine whether or not to grant or deny the petition. This merits review is based on the quality and comprehensiveness of the information contained in the petition, as well as the availability of other information that either supports or contradicts the petitioner's claims. If needed, DTSC may request that the petitioner provide additional information to assist the merits review. And after completing our merits review, DTSC issues a notice of its decision to either grant or deny the petition, along with an explanation for the basis of that decision. Slide 7, please. Presented on your screen is the timeline for the petition that we'll be discussing this morning. In May 2018, the California Stormwater Quality Association, also known as CASCA, petitioned DTSC's Safer Consumer Products Program to list motor vehicle tires containing zinc as a priority product. In July 2018, DTSC deemed the petition complete and started its merits review. In January 2019, DTSC requested CASCA submit supplemental information, which CASCA provided in May of that year. And then finally, in January of this year, DTSC announced its decision to grant the petition. The petition and all the accompanying documents can be found at our CalSafer web portal at the address shown at the bottom of the slide. Slide 8, please. Before we go on, I wanted to talk a little bit about what granting the petition actually means and where we are in the overall process. DTSC's decision to grant the petition does not add zinc in tires to their priority products list. Adding a priority product to the list can only be done through a formal process called rulemaking that government agencies like DTSC use to make new regulations. That currently we are seeking input on our decision to grant the petition prior to initiating the rulemaking process through this public workshop, additional meetings with stakeholders, and our written comment period, which is open through August 6th on our CalSafer portal. Once we receive input and feedback, DTSC intends to begin the formal rulemaking process, which can take up to a year or more. Slide 9, please. DTSC has prepared a rationale document summarizing the...
Okay, can you hear?
Summarizing the petition findings and the reasoning from why we decided to grant the petition. This document, along with the petition, will serve as the basis for our rulemaking. We are currently soliciting public comments on the document and our decision to grant the petition through August 6th. Stakeholders are encouraged to submit comments at our CalSafer web portal at the link shown on your screen. Slide 10, please. DTSC's merits review of the petition focused on two main criteria. In order for us to grant the petition needed to demonstrate that there was potential for motor vehicle tires to expose humans or the environment to zinc, and there's potential for such exposures to cause or contribute to significant or widespread adverse impacts. This is really important, and as Carl mentioned, this criteria is one of the things that sets our program apart from other regulatory programs, where we are looking, because we're taking a precautionary approach, we are focused on the potential for motor vehicle tires to expose humans or the environment. And the potential for those exposures to cause or to contribute to significant or widespread adverse impacts. In the next few slides, I'm going to summarize the information that DTSC determined met this criteria and ultimately led us to decide to grant the petition. Slide 11, please. The petition's claims regarding potential exposure are centered around the exposure scenario, which is presented by the figure you see here. Motor vehicle tires contain approximately 1% zinc. As vehicles are driven, tire tread slowly wears off, creating tire wear particles. These particles wash off roads into storm drains and eventually enter aquatic environments. The petition also includes environmental monitoring data showing high levels of zinc in California's stormwater runoff, the receiving waters that receive that runoff, and sediment at the bottom of those waters as indicators of these exposures. During DTSC's review of the petition and other available research, it was clear that this exposure scenario can and does happen, and that tire wear particles containing zinc end up in our lakes, rivers, and oceans. What was less clear was if the zinc in those particles has the potential to move or transform in a way resulting in exposure to aquatic organisms. As part of our supplemental information request, we asked Casca to provide more information on the environmental fate, transport, and transformation of zinc into the environment and aquatic organisms. In response, Casca was able to provide evidence in the form of laboratory studies showing that zinc can, in fact, move from tire wear particles into the aquatic environment and aquatic organisms. Another part of our evaluation for the potential for exposure was to try to determine the potential for tires to contribute to the levels of zinc reported in the environmental monitoring data. It's really important to understand that the SEC process does not require a product be the only or even the largest or dominant source of a chemical of concern. Only that exposures be not large enough to contribute to adverse impacts. The petition acknowledges that there are many potential sources of zinc in stormwater. The petition claims that in more urbanized parts of the state, major sources of zinc and stormwater runoff are outdoor zinc surfaces such as siding, roofing, and fencing, and tire wear particles. The petition includes calculations estimating that in urban areas like Los Angeles County, the amount of zinc discharged from tires is on the same order of magnitude as outdoor surfaces, with both being in the hundreds of thousands of pounds per year. As part of our evaluation of the petition, we reviewed Casca's calculations and performed some of our own. We also looked at studies from other parts of the country and the world that tried to estimate the amount of zinc discharged from tires compared to other sources. When we did so, we took care to look at each one and determine how applicable they were to the situation in California and account for things like people in the Netherlands driving much less than people here in the United States. Overall, DTSC's review of the petition and the available research indicate tires are a significant source of zinc to California's stormwater, especially in urban areas, and it is likely that a significant portion of the zinc reported in environmental monitoring from that data is from tires. Slide 12, please. The petition presents 3 lines of evidence pertaining to the potential for adverse impacts. First, exceedances of regulatory water quality standards. Second, special handling efforts and required by California stormwater agencies to address those exceedances. And most importantly, laboratory studies showing that California stormwater being toxic to aquatic life with zinc as the cause. With regards to exceedances of regulatory water quality standards and especially handling efforts, the US EPA and the California State Water Board set water quality standards for the protection of water species, aquatic species. The petition states that in many urban areas of California, the water quality standards for zinc are frequently exceeded, both in stormwater runoff and the water bodies that receive it. The petition also claims that zinc concentrations above regulatory limits pose significant problems for municipal agencies subject to stormwater permits. The petition asserts that compliance with water quality requirements can require the expenditure of significant amounts of public funds. While exceedances of water quality standards and specially handling required to mitigate them are possible indicators of adverse impacts under SCP regulations, these claims were not determining factors in our decision to grant the petition. DTSC's main concern is whether or not the levels of zinc actually found in California's stormwater have the potential to adversely impact aquatic life. And a main reason why we requested supplemental information was help us to determine the answer to that question. CASCO is able to provide multiple studies showing California stormwater being toxic to aquatic life with zinc identified as the primary cause. Most of these studies assess toxicity by exposing stormwater to the purple sea urchin, a standard representative model for assessing marine toxicity. Another thing that I just want to point out is that we are not just concerned about effects to the sea urchin. That as a standard representative model of marine toxicity, period, that evidence of stormwater toxicity to the sea urchin demonstrate the potential for adverse impacts in other species. So to summarize, in summary, that DTSC determined that based on the information in the petition and other available sources, that motor vehicle tires have the potential to expose aquatic life to zinc, and that those exposures have the potential to contribute to significant adverse impacts. Once again, we encourage you to provide comments through our CalSafer website. If you have any questions about this work, or you would like to set up a meeting to discuss further, you can email one of the two email addresses below. And with that, we will now take some questions. Oh, sorry, slide 13.
Thank you, Michael. So we'll now be taking some, what's the contact? If you can go to the next slide, please. Oh, that's the, there you go. Okay, so we're now gonna take some questions regarding DTSC's presentation. If you have a question or comment, please click the Q&A button at the bottom of your screen in the toolbar. We'll do our best to respond to questions in the order that we receive them. Once again, we will not be taking questions by chat function, and we ask that you only send one question at a time. If you're joining by phone, please press *9 to raise your hand to let us know you have a question. Or you can go ahead and email saferconsumerproducts@dtsc.ca.gov. We'll go ahead and give one more minute for questions because I don't see any have come in. Okay, our first question says, why is zinc a priority product pollutant vis-a-vis the other surface water pollutants? For example, the number of iron aluminum exceedants require ERA reports in SMARTS for outnumber the zinc. Why is an iron or aluminum source not a bigger priority?
Well, the answer to that question is that this evaluation was a result of a petition that I guess maybe this question might be better posed to Casca, because when we evaluate a petition, it's for a specific product chemical combination, and so we did not evaluate it. It's outside of our scope to evaluate other types of products that contain zinc, other types of stormwater pollutants, or other chemicals that might be in tires as part of the petition review process. We're simply, the intent of the process is to answer those questions on whether or not motor vehicle tires have the potential to expose aquatic life to zinc, and whether or not those exposures can cause or contribute adverse impacts. And that's the scope that's mandated by our regulations.
Thank you, Michael. Next question says, is it up to the tire manufacturers to provide an alternative?
It's up to the manufacturers to perform the alternative analysis. And when they're doing the alternative analysis, they are responsible for identifying the functional performance and safety requirements that are applicable for that product that alternatives need to meet. And as I said before, the reason why we put the onus on manufacturers to perform the alternatives analysis is because they're the ones that know their products the best, and we firmly believe that they're the ones that are best suited to do a thorough and accurate evaluation of the alternatives, so that they're not required to provide an alternative. They are required to assess potential alternatives. So I hope that answers your question.
Thank you, Michael. So I don't see that there's any more questions. I'll give one more minute. Okay. So the next question says, has ZTSC compiled a comprehensive inventory of zinc sources?
No. That's another thing that that would be outside of the scope for the petition review process. That we did do our own research in an attempt to verify or to verify the petition's claims, but that once again, assessing the potential for motor vehicle tires to contribute to zinc and adverse impacts doesn't necessarily require a comprehensive inventory of all zinc sources.
Thank you, Michael. Next question says, is DTSC aware of other efforts to ID alternatives by other groups?
We are aware of some people looking into potential alternatives to zinc or possibly ways where to reduce the zinc content in tires, but part of this process is we're soliciting information and comments, and once again, we firmly understand that a lot of these questions that we're asking are big, tough questions, and there may not be a safer alternative available at this time. And part of the alternative analysis process is, asking the manufacturers to show their work, so to speak, in showing that they really are using the safest alternative that's feasible.
Thank you, Michael. Looks like we may have time for about one or two more questions, but the next one says, what do DTSC studies and research reveal about the loading of zinc from galvanized buildings compared to tires and surface waters? The DTSC rationale merely says significant source, but no quantitative analysis provided.
Maybe I can answer this one, Jessica. I think this is this highlights a part of our framework is that we're not required, nor do we attempt to deal with the most significant problem or to prioritize among different potential problems from different chemicals. So while it would be great if we had all that information about relative impacts from different sources, we don't. But again, as Michael pointed out, we were petitioned specifically for zinc and tires. But even beyond that, if we were to approach every potential priority product from only dealing with the most significant source, we would spend a lot of time and there'd be a lot of debate whether or not we were looking at the appropriate thing. What we do know and what we've documented is that we believe that zinc and tires is a significant source, and we don't have a quantitative threshold. It's a narrative standard. And again, that does admittedly put a burden on the department to use its discretion, but we think we've documented in our document why we think it is significant. And certainly if people think that they have a different perspective, we'd love to hear that.
Thank you, Carl. Okay, so we have one final question before we move on. It says, how would tires from out of state without potential zinc alternatives be mandated if an alternative is required in California only?
Carl, would you like to take this one as well?
Sure. Yeah, so the scope of our authority for these regulations only applies to the sale of these products in California. So if someone comes into California with a car with tires purchased elsewhere, or they purchase tires elsewhere, we have no control over that. So it's really about what we have control over here in California. And certainly I would say that, and maybe Sarah can talk to this later when she talks about the tire industry's perspective. If you look at the work we've done with brake friction materials, brake pads, if you will, both in the state of Washington and California, we both implemented laws to limit metals and other materials in brake friction materials to protect the environment, specifically salmon. And what happened is that we worked with Washington on those regulations and essentially created a de facto standard because manufacturers clearly don't want to have to address 50 different standards. So we recognize that we're out there maybe in front of this, but we can only control what we control in California, and hopefully the marketplace will respond.
Thank you, Carl. So this concludes our Q&A session for DTSC's presentation. We'll now invite Mr. Richard Watson and Mr. Fred Krieger from the California Stormwater Quality Association to present.
May we have our PowerPoint, please? Thank you. This is Richard Watson, and I'm going to provide a little context for the CASCA petition. And and talk a little bit about the functions of our True Source Control Subcommittee. And then Fred Krieger will conclude by talking about a number of the technical and scientific issues related to water quality compliance by permittees. That says slide 15. Go to slide 2, please. This activity that we've got going on True Source Control, we've got this new subcommittee, the True Source Control Subcommittee. The petition that's before you right now is one that started several years ago, and it was under another subcommittee that was dealing with watershed water quality issues on a watershed basis. This current subcommittee really reflects CASCA's vision for sustainable stormwater management. And you see that arrow pointing there to action 1.2, where our particular task in this subcommittee is to work towards minimization of pollution through true source control. And by that, we really mean starting with where the pollutants are and keeping those pollutants out of stormwater, not then having to treat the stormwater at the end of pipe, for instance. Next slide, please. This is a version that doesn't have the page numbers on it. Okay. Is there another button to hit here? But this one is an important issue for us. We did the study back in 2015, and it contains a number of analyses about various sources of zinc in stormwater here in California. We did research elsewhere in the country and overseas as well, and there is quite a bit of data in there about various sources of zinc. We concluded at the time there were two kind of major sources, one being zinc in tires, and the second one being the ubiquitous galvanized metal in the environment. We felt that we had, there is animation, I think, for this slide if you want to click ahead. Maybe that's what's, there you go. One more time. Okay, so we really got interested in the zinc in tires even before the study was done. And we first had, there were a couple of us from CASCA that met with DTSC in the morning on a date back in March of 2011, and in the afternoon met with the tire industry. And we started to become interested in zinc in tires, or zinc period, with the designation of a number of total maximum daily loads in Southern California, and zinc becoming a really critical issue for us. We did consider legislation, but when we were working with the brake pad bill that was mentioned a couple of moments ago, the legislature basically told us not to come back to them for another separate piece of legislation related to a particular metal, but to work through the Safer Consumer Products Program, which was then being developed. And we actually then did comment on the Safer Consumer Product regs as they were developed, and then used this process to come up with the petition. Yeah, I think that's all I need to say about that one. So we chose to do the Safer Consumer Product approach, as I mentioned, and these regulations became effective in 2013, and then we started working on this process. Next slide, please. Okay, the goals of our petition, we really wanted to eliminate or reduce zinc as a water pollutant by focusing on a major source, and this was zinc in tires. We chose zinc in tires because it seemed more manageable through this process than trying to deal with the very widespread galvanized metal in the environment. So we also wanted to facilitate compliance with MPDS permits issued by state and regional water boards. These are municipal stormwater permits, and they're industrial permits and others. So we did then submit the petition to demonstrate the potential for exposures and adverse impacts. Next slide, please. The Clean Water Act contains this so-called 303D list requirements, and this is a designation of impaired waterways, and it's by segment and pollutant combination. And there, zinc in tires, or zinc in particular segments, particularly in the urbanized area, has become important. If you look at the rural areas of the state, it's not as much of a problem. But in the metropolitan areas, zinc and other things like copper are very significant problems. And so there are a number of listing factors that are involved in the state's listing, delisting policy. And so we were considering all of that and how we would address that. Next slide, please. I mentioned total maximum daily loads a couple of minutes ago. These are the results of things being listed on the 303D list. The requirements are that once things are listed, the regulatory agencies are supposed to develop maximum daily loads, total maximum daily loads, or TMDLs. And those TMDLs allocate what are generally considered safe loadings from various sources of the pollutants. And then they became really significant drivers for a lot of activity, a lot of regulatory processes. And you see a number of the sources listed there. Next slide, please. So one of the problems that we have is we've got two things. We've got the TMDLs I just mentioned, where permittees are generally regarded as the municipal permittees as the major sources. They have the responsibility for their land uses and the roads, et cetera, in their areas. And so the regional boards assign that responsibility to the municipalities. But at the same time, there are what are called receiving water limitations. And these contain the same language that was discussed earlier, except that they don't have the word significant in there. So discharges shall not cause or contribute to an exceedance of a water quality standard. So that's a very tight limitation. And then you have the TMDLs, which are really driving a lot of the process in California now. Next slide, please. And I'm going to now turn it over to Fred.
Hi, Richard. Thanks. Can you hear me? Yikes.
Speak up a little bit.
Okay, how's that? Okay. Let me get the slides up. The key numbers that we're concerned about for regulatory compliance are the water quality standards. The inland waterway standards were promulgated by US EPA back in 2000 statewide. The ocean standards were issued by the State Water Board. Now, I should note that the freshwater standards vary depending on the hardness of the receiving water. So if the receiving water has a high hardness, the applicable standard is higher. Now, as Rich pointed out, dischargers of stormwater are required to comply with these numbers, generally at the point of discharge. And TMDLs that are developed to bring a whole waterway back into compliance also target these numbers. The next slide. Now, currently, zinc is a significant component of urban stormwater runoff. Now, the LA River, for example, also has discharges from sewage treatment plants and industries, but stormwater contributes 90% of the zinc loading on an annual basis. And that's pretty amazing considering that the sewage treatment plants and industries may be discharging year round. Next slide. Okay, does this zinc in stormwater cause compliance problems? Yes, in this sampling by the Los Angeles Flood Control District, all in-stream samples from waterways in mostly urbanized areas exceeded the standards. The more highly urbanized areas are those with a lower percentage of vacant land, those top four sites. The evaluation of these samples, which was on the receiving water, took into account the receiving water hardness. Next slide. Now, are tires a source? Now, we looked at various bits of data, but this seemed particularly compelling. Caltrans sampled stormwater as it left the pavement. Now, tires are the major source of zinc in this pavement runoff. We did look at other sources, and those are described in the petition and the supplement. Now, about 20 years ago, Caltrans did a comprehensive statewide sampling of their stormwater runoff. And based on that sampling, they estimated that total zinc exceeded the standards 87% of the time, and dissolved zinc exceeded about 52%. Next
Fred?
slide. Oh, yes.
Can you speak up a little bit? Some people are having trouble hearing you.
Okay, how's this?
There.
Is that better? Let's see.
Yes, go ahead.
Okay, next slide. Okay, so we know that the regulatory standards are exceeded by zinc in stormwater, especially in urban areas, but is it impacting aquatic organisms? Now, to make this determination, it's necessary to do a study called the toxicity identification evaluations. These are fairly expensive and difficult to implement, but 2 of these were done in Southern California, and they indicated that the toxicity most likely came from zinc. Next slide. An additional concern we have is that in California, Caltrans is required to use crumb rubber, which currently contains zinc, in paving projects. This crumb rubber has certain benefits, including for safety, so it's generally beneficial. However, it can also increase the amount of zinc in runoff. Next slide. Now, this slide shows the results of 2 studies in Texas. In one case, the crumb rubber, they did not use crumb rubber, and there's still zinc due to the tires on the road surface. Those are the green bars, but the red bars are the runoff, or is the runoff from the location where the crumb rubber is added to the paving mix. So using crumb rubber, which is mandated, does present a significant risk. Next slide. Now, CASCA is focused on source control as the best option for addressing probably most of the pollutants in urban runoff. Now, for copper and lead, source control is already making a difference. For zinc, however, we haven't had source control, and capture and treatment of stormwater is simply not feasible for most urban stormwater situations. It'd be extraordinarily expensive and disruptive. So new standards for zinc might help somewhat, but we know that we already have aquatic impacts due to the zinc that is present out there. So we need source control because we currently have these aquatic impacts. The next slide. So is it really feasible to reduce the amount of zinc in tires? Now, back in 2005, there was an article indicating that Michelin was looking at ways to significantly reduce the amount of zinc in tires. So that looked promising. We also found several patents assigned to the tire manufacturers for ways of manufacturing tires with less zinc. So that looked like that may be a way that we could reduce the loading. Next slide. So we believe that CASCA, DTSC, and the State Water Board working together can make a big difference in controlling pollutants, including zinc, through source control. And that's it.
Thank you, Mr. Watson and Mr. Krieger. Next slide, please. We will now take some questions regarding their presentation. Again, if you have any questions or comments, please click the Q&A button at the bottom of your screen or press *9 if you are a phone caller. You can also email Safe for Consumer Products. So I'll go ahead and give a moment for people to ask their questions. Okay, it doesn't look like we have any questions. Give one more moment. All right, so we have one question. It says, was the disposition reviewed in the EDGE or EDG-EOF pavement monitoring?
I'm not sure what that means.
Oh, sorry. It says, was the disposition reviewed in the edge of pavement monitoring? Sorry.
Oh, the edge of pavement monitoring. You mean, where was the water eventually disposed of? So, go ahead.
Just says,
I think it's deposition, not disposition.
oh,
Was deposition reviewed in the edge of pavement monitoring?
I think that, I'm not sure. I would guess that didn't matter. They were just trying to find out how much came off the road surface. So at the very edge of the pavement, they took their samples. Now, afterwards, that runoff could have gone into a drainage and into a waterway, or it could have been just disposed of on land.
Now, this is Rich. I would add to that too. Fred showed that graph with the data from Texas, and Mike Barrett had done work out here in California too. So I think you had a general interest in this whole idea of to what extent was zinc coming off the roads, and how much was from tires, and how much might be from the rubberized asphalt.
great. Next question says, do you know if there are studies looking at the contribution of zinc in stormwater from outdoor storage use or outdoor storage of used tires?
No, we didn't find anything along that line. We did look at zinc, other zinc sources or zinc exposure, where crumb rubber, for example, is used on playgrounds and other places. However, just because of how playgrounds are constructed, it didn't look like there would be significant runoff from them. I guess in some locations, if you had a large pile of tires, yes, that might be an issue.
But I think another factor in that is it wasn't a water quality issue at the time they started this, but it was the dangers associated with fires in big piles of tires, et cetera. And that started a lot of the recycling emphasis on tires to take care of those. So you don't have, at least in California, you don't have that many large piles of tires because there's an extensive recycling program.
Thank you. Next question says, RMA has made several iterations and processes to become much more viable. Do you have any data more current for zinc leaching from rubber modified asphalt?
Yeah, that chart that we showed from Texas. I mean, that was quite striking, actually. The increase. So there's zinc coming off the roadway from tires. But when they added that rubberized asphalt, the zinc increased substantially. Some of those loadings were kind of shocking.
Okay, it looks like that may have been our last question. I'll give one more moment before moving on. Okay, we have another one. It says, CalRecycle has performed a study on zinc from rubber mod asphalt, and the results will be out soon. The preliminary results from our understanding show no ink and zinc from rubber modified asphalt. Is DTSC aware of this study?
I'll try and answer that. If the crumb rubber is used on the friction course, which is the uppermost layer of the asphalt, then I think it almost certainly will contribute zinc. If it's used in other parts of the asphalt in lower levels, then it probably would not. I have not seen that most recent study, however.
Let me just chime in a little bit. We are aware of the study. Our colleagues at CalRecycle have made us aware, and we've reviewed it and commented on it as well. So, yeah, we are aware of that. Thank you.
Okay, our last question says, what are DTSC's recommendations for Caltrans or commercial parking lots, high traffic areas?
That sounds like a question to DTSC, not to us.
Again, I'll chime in on that. I think, these are good questions, but most of them are outside the scope of our focus right now. Certainly, as more information is made available, we share that with our colleagues. And if they have questions, we're happy to engage. But we haven't actively engaged with Caltrans on that issue.
Thank you, Carl, and thank you, Mr. Watson and Mr. Krieger. This concludes our Q&A for their presentation. I would now like to invite members of the United States Tire Manufacturing Association, Sarah Amick, Julie Penko, and Howard Colvin to present.
Great, thank you. And you'll pull up our slides. Great. Well, thank you to DTSC for the opportunity to provide comments during this workshop. We greatly appreciate and welcome the opportunity to be engaged on these important issues. If we can go to the next slide. So just a little bit about who is presenting with me today. I'm Sarah Amick. I'm the Vice President for Environment, Health, Safety, and Sustainability and Senior Counsel at the U.S. Tire Manufacturers Association. I'm joined today by Howard Colvin, who is an expert polymer scientist and an independent technical consultant to USTMA. And I'm also joined by Julie Penko, who's a principal scientist at Tox Strategies and also is a consultant on behalf of our association as well. And we can go to the next slide. So just a little bit about the U.S. Tire Manufacturers Association. Who are we? We're a Washington, D.C. based trade association. We represent 13 manufacturers, tire manufacturers that produce tires in the United States. All of our members are committed to sustainable practices in every aspect of their businesses. And USTMA members collectively embrace a shared responsibility of helping to achieve a more sustainable society. Our members work to engineer products that reduce CO2 emissions, enhance tire safety and performance, drive progress in workplace safety, and preserve the environment throughout a tire's life cycle. And you can learn more about our common vision on sustainability at the website I've included at the top of this slide. We can go to the next slide. So what we'll cover today, we'll provide an overview of, from our perspective, what's actually needed to address zinc water quality issues in California. We'll provide an overview of tire materials and tire manufacturing. We'll share information about the role zinc oxide serves in manufacturing safe tires. We'll provide an overview of why we believe zinc in tires does not meet the criteria for listing as a priority product. And last, we'll reiterate our request that DTSC pause work related to zinc in tires to allow the biotic ligand model to be implemented, and I'll talk a little bit more about that. And we can go to the next slide. So starting out from our perspective, what is needed to address water quality issues related to zinc in California? And we can go to the next slide. I just want to set perspective. USTMA has been engaged with the California Stormwater Quality Association, the International Zinc Association, and also the California Water Board since 2016. And I want to mention, I think Richard mentioned part of the story, but the other part is that in 2016, the California Water Board picked up a project under the STORMS program to assess whether they should be the ones to file, or whether there was a need to file a petition to review zinc in tires under the Safer Consumer Products Regulation. And IZA, CASCA, and USTMA spent several years talking with the Water Board about issues related to zinc and zinc in tires, and worked together collaboratively on approaches to help resolve zinc water quality issues in California. The Water Board ultimately decided not to file the petition, but CASCA did. And even before the petition was filed, there's a quote here from Fred from 2017, Fred Krieger, who's a consultant to CASCA, that said, even if approved, a DTSC-based zinc phase-out will not impact zinc in runoff in a timely manner and allow dischargers to meet the TMDL final waste load allocations. So 4 years ago, CASCA consultants admitted that sending zinc in tires through the Safer Consumer Products regulatory process will not actually resolve issues related to zinc water quality in California. And we can go to the next slide. So what is needed to address zinc water quality issues in California? If we take a look at how water quality criteria are currently established today in the state, we see that California is using old models to establish water quality criteria for zinc. And the existing hardness standard that is in use in California does not represent the best available science in setting water quality criteria. And science has evolved to utilize sophisticated new water quality models, such as the biotic ligand model, which take into account significant factors like bioavailability. And the International Zinc Association will be speaking more on this point in their presentation. And we can go to the next slide. So this is a slide that IZA may actually be repeating in their presentation, but I think it's worth noting here an important point. If we look at all of the existing water data we have in California, and we apply the hardness standard, which is the bottom right quadrant of this chart, we see there's over 157 samples roughly that show impairment using outdated science. If we put in place the biotic ligand model, which represents the best available science for establishing water quality criteria, we show that only 2 water bodies in the state show impairment for zinc. And it's important to note that neither of these water bodies showing impairment are in the LA water basin, where initial concerns around zinc were raised. And I know the IZA will speak more on this point. So we can go to the next slide. So with this in mind, USTMA strongly recommends that the Safer Consumer Products regulatory process should not operate in a vacuum, that addressing water quality criteria for zinc in California requires a different approach, and that's using the best available science to establish water quality criteria. And we strongly recommend that the State Water Resources Control Board and the LA Water Board implement the biotic ligand model for zinc. And we know that the LA Water Board is currently working to implement the biotic ligand model for copper and recommend that they also include implementation of the biotic ligand model for zinc. And if results after the BLM has been applied to assess water quality criteria in the state demonstrate that California does not have the widespread adverse concerns around zinc using the best available science, our recommendation is that DTSC then remove zinc in tires from the work plan. And we have been and will continue to welcome the opportunity to work with California regulators to advance the best use of the best available science and implement the biotic ligand model. And we can go to the next slide. So now I'm going to turn it over to Howard Colvin. Again, Howard's a polymer scientist and a real expert in tire manufacturing, to talk through a bit of the background of the functions of a tire, how tires are regulated, tire materials, and the critical role that zinc oxide serves in producing safe tires. So Howard, take it away.
Thank you, Sarah. Can everybody hear me okay?
Yes.
Okay, great. I appreciate the opportunity to talk about this important topic and appreciate your time. The next slide, let's go to the next slide here. I'm not going to go through all these individual things. I will say a couple of things, though, to start with. We all buy tires, and as such, we expect tires to perform, and we really don't like to think about tires. I personally, as a consumer, don't want to think about tires, but if I do stop to think about them, I really ask my tires to do a lot of contradictory things. For example, if I'm driving down the highway, I expect to have very low rolling resistance. I want no loss of energy. I want good gas mileage. But when I hit my brakes, I expect all the energy of the tire, all the energy of the car to be immediately converted to heat. And basically, my tires will have to function as the only part of the car that's in contact with the road to be able to do that function. Those are contradictory functions, but with what the industry's been able to accomplish, we've been able to do that and a lot more, and to do it safely. And the key thing for us is tire safety. Next slide, please. So how are tires regulated? Next slide. And again, as we pointed out, safety is the priority. We have a very highly regulated product. to ensure consumer safety. The NHTSA regulates new tires, and we have the Safety Act also, which has an impact here. And it's important to realize that as we change tire materials, whether this is done by the legislature demand or whether the tire company tries to improve the performance, all areas of the tire will be affected, and the tire has to undergo significant testing before it can be released to the public. Next slide, please. Okay, and here are some of the FMVSS standards that we must meet. And again, I'm not going to read through all these. Again, it points out the state of the regulation that the tire industry is under. Next slide, please. So how do we make a tire? And I think it's interesting just from a science standpoint, but also I think for this particular group to understand how a tire is made and how zinc oxide plays a role in that. Next slide, please. Okay, when we look at a tire, and I'll make a comment that was made to a company I worked for. It was a major OEM auto manufacturer, and his comment was that on the car, the most engineered part of a car is the tire. And you can see from this slide why he might make that statement. We have 10 to 15 different rubber compounds in a tire. Each one of those compounds have different polymers, different curatives, different oils, all designed to meet a specific function for that particular component. And these are not only different by the type of component, each company has their own take on this, and each company designs these compounds to fit in the holistic tire, their particular tire. In a tire, we use anywhere from 45 to 60 unique materials, and you can see the various parts of the tire here and the way that the tire is constructed. It's not only the materials that go into the tire, but it's the way that the tire is put together, the timing, the adhesion. There's a lot of factors that go into the manufacturing process that we won't have time to talk about today, but it is a very complicated process that we undergo. Next slide, please. And again, this is sort of a summary of what we see in a tire. We have rubber, synthetic and natural. We have processing age, so it will flow in the plant. We use fillers for strength. We have antioxidants for protection, which allows the tire to last during its normal lifetime so that it will wear out by loss of rubber rather than failing prematurely. We have textiles such as polyester, polyamides, which help with the reinforcement. Of course, we have steel belts, which provide a great deal of reinforcement. And the curing system, and this is the area that the zinc oxide plays a very important role in. Next slide, please. Here's an example of one of those many components that we talked about. This is a typical tread formulation. Now, the tread has more rubber in it than almost any component of the tire. And here we have the percentages of the rubber, the filler, the other process additives here. And notice the level of zinc. This level is absolutely critical, or let me say the zinc oxide is critical to the performance, but the actual level used in the tread, as an example, is quite low. Next slide, please. And to get down in the weeds just a little bit more, the way that we convert a tire, which is just sort of a gooey mass of rubber and filler and everything else that you could take in your hands and pull out, the way that we convert it to a hard tire, the final product, is we undergo a process called vulcanization. And this is where we take the uncured or the green rubber to the cured state by forming chemical crosslinks. And this happens in the tire mold. And this gives the tire the strength, stability, and the elasticity, which allows it to wear, to have stopped very rapidly in the wet and the dry and the snow, and to be durable. The diagrams on the right show an uncured and a cured polymer sample. What happens in a polymer without crosslinks? This particular polymer, if you were to put it on this piece of paper, it would flow. It's a process we call cold flow. It's like a slow motion spilling your syrup, but it would flow. Once you cure it, once you vulcanize it, you have a hard rubber. And in the case of a tire, you have a rubber article that has all the properties that we expect of a tire as a consumer. The key thing that we need to understand here is that we have the cure package. We'll talk about that in just a moment. We have the structure of the rubber, which has double bonds in it. And we have the zinc. And the zinc plays a very important role and to converting it into a hard rubber, useful rubber. Next slide, please. Okay, this illustrates what we call the cure. And if you look at this graph here, we're graphing time for the cure to take place on the x-axis and the state of cure on the y-axis. And notice here, if you, in the time period that's needed for curing a tire, if we only had sulfur, very little cure would take place. If we add the sulfur and the accelerators, more cure takes place, but we don't achieve the properties in the tire that we need to have a suitable consumer product. It's only when we add the sulfur, the accelerators, and the activator, which zinc is a part of, where we get the performance requirements and the safety requirements that we need to sell our tires. So the curing system is required to ensure the proper cross-linking here, and the use of the zinc oxide provides an optimized cross-link network. Next slide, please. And let me say that zinc oxide is critical to tire safety. The reason that we use zinc oxide is because it activates and promotes the optimum number and type of crosslinks. And I'm not going to go into the detail here, but it's not just the number of crosslinks that play a role, it's the type of crosslinks. And if you have the wrong type of crosslink and the wrong component, you will not get the performance that you need to have a safe tire. Zinc plays a role in both of those things. It gives us the strength, the stability, and the useful properties for every component in the finished tire. It's a critical ingredient that allows the tire to perform safely, and without zinc oxide, with current technology, we cannot manufacture tires to meet the safety and performance standards. Next slide, please. Okay, I'm going to turn this back over to Julie for her comments.
Hi, everyone. Thanks, Howard. Yes, I'd like to take the next few minutes to talk a little bit more about how zinc enters the environment from tires. Next slide. So Michael alluded to this early on with respect to DTSC's evaluation of zinc in tires. And I wanted to talk a little bit more about the tire wear particles that he mentioned. So as Howard said, the tires are really one of the most important safety components on a vehicle. You know, they have to do all those things that Howard mentioned. They have to support the weight of the vehicle. They have to help the vehicle withstand impact. They have to perform in all kinds of weather conditions. And also, as Howard mentioned, tires are the only point of contact between the vehicle and the road. And because of that, the grip that the tire has on the road is really critical because it prevents you from sliding off the road and being safe. And this gripping action causes abrasion of both the tire tread as well as the pavement. And when that abrasion happens, tire and road wear particles are formed during that process. And that is a mechanism for zinc in the tire tread to enter the environment. The pictures on the right side of the graph here are microscope pictures of what these tire and road wear particles look like under the microscope. And as you can see, TRWP, we call them TRWP, are really a mixture of the tire tread and the embedded pavement. And since about 2005, USTMA members have been engaged in research to better understand these particles in the environment, and have supported a variety of scientific studies that have been published in the literature to characterize the particles and understand their potential impacts in the environment. Next slide. So in answer to Carl's statement about whether or not anyone agrees with DTSC about whether or not zinc from tires is a significant source, I wanted to take an opportunity to walk through that criteria and why USTMA doesn't believe that zinc from tires meets the criteria for listing as a priority product. Next slide. So as Michael mentioned, there really are two criteria for listing a priority product. The first is that there has to be a potential for exposure to a chemical from a product, and that product must contribute or cause significant widespread adverse impacts. And so Sarah touched a bit on whether or not these impacts are truly occurring based on the current water quality standards, but there's also this topic that we've sort of touched on both by DTSC and by CASCA, and that is, the sources of zinc in the environment. So there are really three main points here on why we don't believe that zinc should be considered a priority product. The first, of course, is that there are many sources of zinc in the environment and many sources of zinc that can reach stormwater. Second is that zinc is not really very bioavailable from tire wear particles. And third, we think that the CASCA petition mischaracterizes the zinc release from tires based on the Caltrans study. So I'll go through each of these. Next slide. So first, regarding those other sources of zinc in the environment. So people have talked about galvanized sources, but there's really three overall sort of buckets or categories of zinc sources in the environment, each of which may end up in stormwater or released to surface water. The first one is a pretty big bucket, an important bucket of construction materials. And this is where those galvanized metal surfaces come into play. So it's not just roofing and siding, but it's road barriers like guardrails, it's light poles, it's fences, it's all of those things. The second big bucket is consumer products, and a variety of literature have identified littered products like batteries and just coins as important local sources of zinc that reach stormwater. And then, of course, vehicles are in this category, including tire wear, but also brake wear, which has zinc in it, as well as engine exhaust and different kinds of engine oils. Then the third big bucket is really zinc released to the environment, primarily through air emissions, and those can come from combustion sources as well as industrial emissions. And also, zinc can reach stormwater from soil runoff, especially from agricultural areas where zinc might be used as an herbicide or pesticide. Next slide. So although Carl mentioned that DTSC is not required to do an inventory, they're only required to look at the merit of the petition, where other jurisdictions have conducted a comprehensive inventory of zinc sources to watersheds, they find that when they quantify tire wear, it's usually a fairly low contributor, generally around 10%. I listed some of the inventories that have been conducted. In particular, Washington State conducted an inventory and concluded tire wear contributed only about 12% of zinc loading in the urban runoff. Similarly, and Carl mentioned the Netherlands study, or Michael mentioned the Netherlands study, only about 8% was attributed to tire wear. So we do think a comprehensive inventory would show that zinc from tires is unlikely to be a significant contributor causing widespread harm. Next slide. In the CASCA petition and in the CASCA report, the Davis et al. 2001 study is mentioned as an example of a watershed inventory or an inventory in an urban area. And you can see the pie graph on the left. This is from the Davis study and is showing zinc runoff in urban residential areas that have brick buildings. So there are many different varieties of areas that they looked at. And in this case, siding, in fact, galvanized siding was contributing about 59% to the runoff and tires only 25%. USTMA took those calculations and updated them with current wear rates that are specific to the different types of tires and reran those calculations, looking also at the potential for, what really gets washed off of the road, what stays on the road. And when you redo those calculations with current information, you find that tires in that study would have only contributed about 10% to the urban runoff. Next slide. I also mentioned that zinc from tires is not really bioaccessible to the organisms. There have been several studies conducted where researchers were specifically looking to measure the amount of zinc that can leach out of tire and road wear particles or just tread particles. And they find that is pretty low. 0.1 to 4.5% of the zinc is available from the tire wear. The researchers have also found that salinity and pH also affect the amount of zinc that would leach out. So if CASCA were to rerun their calculations, and we have talked about this in those meetings that Richard mentioned, and account for the bioaccessible fraction, you would find that zinc from TRWP is very low. Next slide. And then our last point regarding the contribution of tires to zinc and stormwater loading. The CASCA petition relies heavily, as Fred mentioned, on the Caltrans, what they call edge of pavement study. CASCA indicates that tires were the only source of zinc in the stormwater runoff. However, in contrast to that claim, the study design actually did not exclude other sources of zinc, including galvanized structures and guardrails along these roads. And in fact, Caltrans found that there were factors other than traffic and precipitation that were contributing to the zinc concentrations. Similar to Fred's slide on the Caltrans data, this is a reorganized table where I've listed the highest concentrations first. So Moreno Valley, Yorba Linda, and Irvine had the highest dissolved and total zinc concentrations. And if you go to the next slide, and you take a look at the photos from the Caltrans report of Moreno Valley, of Yorba Linda, and of the Irvine location, you can see that in each case, each of these sampling locations is bordered by galvanized surfaces. In Moreno Valley, you can see clearly that there is galvanized fencing along the edge of the sampling trough. In Yorba Linda, the water is being collected almost immediately under a very large signpost or light post, as well as by the guardrails. And then there in Irvine, the collection system that was constructed leading from the road, you can see right above the road, there is a guardrail there in the background, as well as a lamppost or a signpost behind that car. So for these reasons, we don't believe that the Caltrans study supports CASCA's conclusion that the zinc in these samples came from tire wear. Next slide. And I think I'm turning it over to Sarah at this point.
Thanks, Julie. So I mentioned it at the beginning, and it's worth mentioning again. we strongly recommend that the California Safer Consumer Products Regulation should consider actions and the ability of other state agencies to address issues around water quality, particularly on zinc. And we strongly recommend that DTSC pause work related to zinc in tires to allow time for the State Water Resources Control Board and the LA Water Board to implement the biotic ligand model for zinc. And if utilizing this best available science demonstrates that California does not have many exceedances or over 2 or significant exceedances for zinc water quality, that DTSC should remove zinc from tires from the priority products work plan. And we have been involved in this issue again since 2011 and really working with CASCA and IZA and the Water Board in 2016, 2017 and beyond. We will continue to help to support the biotic ligand model, and we welcome the opportunity to be a resource on that. I want to thank DTSC again for the opportunity to present today, and we're happy to take any questions folks might have.
Thank you. Next slide, please. And one more, please. Alrighty, so now we will go ahead and take some questions regarding United States Tire Manufacturing Association's presentation. Once again, you can click the Q&A at the bottom or press *9 to raise your hand if you're joining by phone. I'll give a couple moments to allow people to input their questions in the Q&A. Okay, our first question says, how comparable are Washington and Netherlands studies to California environments, considering the Washington study included zinc used for moss control, for example?
Julie, maybe you're best suited to respond to that question.
That's true. Washington did find that moss control was the one of the largest sources. I would say comparable in that the Washington study did look at an urban environment, and I don't have any reason to believe, or I don't really know, if there's big differences in traffic volumes in local areas or not. But it is a study that was done here in the United States. It was comprehensive in terms of all of the sources that they looked at.
Okay, thank you. I don't see any more questions at the moment, but I will give another moment before we head to break. Okay, we have one question that says, zinc from tires become more prevalent if the tires are not replaced in the appropriate time. In other words, could zinc be detected in more communities of lower socioeconomic status because they are not able to afford replacement tires in the correct time frame?
I think this is speaking to the contribution of tires from tire and road wear particles. I think Julie's probably also best suited to respond to this question as well.
I think that, zinc is prevalent, and Howard may have to jump in here too, throughout the tread mixture. So as long as there is wearable tread, there is a zinc as part of the tread. So I don't believe that there would be necessarily more zinc released in communities that use their tires longer. I don't know, Howard, if you have an opinion there.
Yes, I think that the zinc would be uniformly distributed in the tread. You wouldn't expect any striations of zinc in the tread. So yes.
And I think, Julie, too, the research shows that the bioavailability fraction from tires is relatively low.
Okay, thank you. We have one final question before we go to break. It says, for the biotic ligand model, what species are the bioavailability data derived from? This is important for the interpretation of the model results.
So I think the International Zinc Association is definitely going to touch more on the biotic ligand model for zinc. So I would defer to Eric and Adam to be the experts in responding to that question in their presentation.
Yeah, thanks, Sarah. We will do that, but just for this question in particular, we don't have as much time to present during our session, but the current biotic ligand model we use for criteria derivation is built from species-specific information for fish, both cold water and temperate, for insects, snails, rotifers, daphnids, and even algae. So it is comprehensive in terms of its coverage of those three taxonomic groups.
Great, thank you for that. So this concludes our Q&A session on the U.S. Tire Manufacturing Association's presentation. We will now take a 10-minute break and resume at 10:40. Next slide, please. Thank you for joining us as we return from a short break. I would now like to invite Dr. Kelly Moran from the San Francisco Estuary Institute to present. Next slide, please.
Thank you for the opportunity to provide an overview on how tire particles and the chemicals within them reach California's aquatic environments. I should note right at the front, this is a presentation that's generic. It is not specific to zinc, and it's applicable for all three of the workshops that DTSC is holding. Next slide, please. Tire tread wears off during use. We've been talking about that in the prior presentations. Just to give a sense of this, based on the literature, an estimate for the US is that 3 to 5.5 kilograms of tire wear material is released per capita, is released into the environment. So that includes not only personal driving, but also deliveries, food, all the other kinds of things that happen to support us through our lives. These particles are really tiny. So they're well under micron size, some of them all the way up to about 100 microns. So these are at a very small size range, which makes them easy to move around in the environment. Next slide, please. So tires contain more than rubber. So I appreciated the prior slide, which reviewed in more detail tire formulations. The tire chemicals that tend to be of interest from the environmental perspective are those in the bottom three categories on this slide that are shown with the shading. And what I want to note is, as mentioned earlier, there are many different formulations of rubber within tires, but the tread material is of greatest interest because that's the material that wears off and is so widely dispersed into the environment. It's also very important to note that manufacturers have different formulations, both for from each other because their formulations are proprietary and because their tires serve different purposes. So a lot of studies have been done that just looked at one or a small number of tires, and those would not be considered representative of all the tires on the road. Similarly, aging affects the chemicals because many of them are used or basically sacrificial chemicals that are designed to react with other chemicals in the environment. So aged material will be different than virgin materials. Next slide, please. So another thing that has happened in a lot of the literature and something that's really important to keep in mind about tires is there are particles of tires. So a lot of people are researching and are interested in how tire particles move through the environment. And then there are also chemicals that are in tires that can be released from the tires as through their whole life cycle. Next slide, please. So really, these are one and inseparable. So it is really difficult to understand and interpret a lot of data that are out there because tire particles and the chemicals they contain cannot be separated. If you're testing tire particles, you are inherently testing the chemicals within them. So once the chemicals are leached out, they can, of course, be tested separately, but they move through the environment carrying these chemicals. Aquatic organisms can be exposed to either the separated chemicals in water or the tire particles, which then have the potential to release the chemicals. This makes interpreting the data also very difficult because many people are trying to look at various types of tire particles and their potential effect on aquatic organisms. And as they're doing it, they're inherently testing the chemicals within them, which may be specific to the formulation of the tire or a small group of tires that have been tested. Next slide. So why in the big picture do people care about this? So tire pollutants and tire wear particles wash into storm drains. We've had detailed discussion of that already. These storm drains flow directly to surface water without treatment. And in California, there's only 2 small areas where stormwater flows to a sewage treatment plant. This is important for the California analysis of this. Both the particles and the leachate have been found to be toxic to aquatic organisms, and there is the potential to harm fish and ecosystems as a result. Next slide, please. So I really want to emphasize that California stormwater flows directly to surface water without any treatment. Many of the studies in the literature, and in fact, most of the literature that is out there is in regards to places where stormwater flows into a sewage treatment plant before being discharged, thereby removing most of the chemicals and the particles before discharge. And it causes the discharge to shift to a sewage treatment plant flow instead of to scattered pipes throughout communities. So this is very, very important for the California context. Next slide, please. So tire particles are the most common microplastic flowing into San Francisco Bay. My colleagues at the San Francisco Estuary Institute completed a study of microplastics entering San Francisco Bay from all of the various sources and then within the water, sediment, and prey fish and bivalves. The study found that tire particles were the most common microplastic identified. And I need to emphasize that the study design likely significantly undercounted tire particles. The method used only caught the largest particles within the particle size distribution, and the separation techniques, particularly for prey fish, bivalves, and sediment, did not account for the additional density. So basically the traditional microplastic separation technique will leave the tire particles that have road material attached to them behind. Next slide, please. So here's a picture of that. There's black circles here that are magic marker markings under, this is a microscope photograph. And the black material in the on the slide inside the circles are black rubbery particles that are identified as tire wear material. Next slide. So one of the very important issues in understanding both the particles and the chemicals within them is the relationship between surface area and leaching potential. So wear particles, those formed by frictions, for example, brake wear debris and tire wear particles, will have a lot more surface area than standard laboratory testing materials. This is sort of an overstatement of that with the ball, but powders and other kinds of materials tend to have a relatively small surface area. The surface area of a wear particle can easily be 100 times greater. Next slide, please. So here's a photograph of a laboratory generated wear particle for tires just to show, illustrate the great surface area that may be available on these particles. This is a scanning electron microscope photograph. The lighting here isn't that it's generating anything interesting. It's just the artifact of the imaging process. There are other data such as the measurements, the various other bits of literature that give us a clue that there is a lot of surface area of these particles, but we've been so far unable to identify measurements of the surface area of them covering the particle size range, that's the full particle size range that's emitted when tires are used. Next slide, please. So most tire wear particle mass winds up near roads, but small particles can fly far away. So this matters a great deal. So here, looking at the image, what you see is the great artistic taxi cab with showing the various forms of emission. So first, there's wear that occurs as a result of the road. It appears based on the particle size distribution and the characterizations in the literature that there are actually multiple formation processes. And that may relate to the size of the particles. So different things are happening, creating different kinds of material. The material is so that some of it is emitted directly to the air, and the smallest particles may leave the watershed and fly enormous distances. So this can explain the detection of tire-related chemicals and materials in distant global locations. Material that falls on the road may be blown to the side of the road. Some of it might be ground into pavement. A lot of it is subject to further action by the vehicle one way or another. This is how you get some of these rolled particles that folks see. Most of it winds up based on chemical analysis within about 10 meters of the road, which happens to also be where most directly connected impervious area is. And that's the stuff that will be most likely to wash off right away. So as I mentioned, the surface area is really important. So even though most particles are the larger size and they fall within about 10 meters of the road, the tiniest particles will have the most surface area. In general, tiny particles have more surface area than large particles. Now, which segment of the particle size distribution has the most surface area is currently unknown. So we do not know if most of the chemical release or a huge majority of it, or maybe just a small fraction of it, is it represented by the tiny particles that go up into the air, as opposed to the larger mass particles that land close to the road. This makes a huge difference in terms of environmental exposure. Next slide, please. So tire-related chemicals are released everywhere, and this is a really fascinating data set that is still growing. There's several chemicals that have been used as indicators of the presence of tire material, although tire chemicals used in tires all have other purposes, as we're talking about here today with zinc. But tire particles and their chemicals have been found in environments all over the world. And interestingly, very interesting, that tire-related chemicals are found dissolved in stormwater. So that means that particles, the wear debris, is deposited in the urban environment, and there's enough surface area to very quickly, on a very short exposure, because a runoff occurs during a rain event, to release those chemicals into the water. And there's multiple studies showing that occurring, which gives a sense of this very large surface area that I mentioned. These tire chemicals are also likely to be released from the particles as they move through the transport system. So not just the chemicals themselves, but the particles are also transported. So they'll be in creeks and rivers, in estuaries, in the ocean, in sediments, and there's a proof of organism uptake of the particles. So in all of those locations, the tire chemicals are likely to be released. Back on the surface area, one thing I do want to mention is that the surface area of the particles, although not measured, is likely to be much greater than the surface area of the standard particles that have been the subject of most of these leaching tests. So often they're cut up pieces or cryomilled particles. So it's very difficult to interpret the literature in terms of leaching and bioavailability. The stormwater data are incredibly unusual and compelling, that we're seeing releases of chemicals from particles that are deposited in watersheds, and we're seeing it released in the dissolved form into stormwater. Next slide, please. So I just want to wrap up by saying that many potential mitigation options exist. These are theoretical mitigation options, but I do want to note that the conversation has largely focused on two sets of mitigation options that do have long timeframes, as was mentioned in the quote from Fred Krieger earlier. So today we're having conversations about the potential for adjusting the formulations of tires. That's removing toxic ingredients out on the prevention side. And there have been many conversations about the idea of capturing and treating all urban runoff to remove the contaminants. That's something that I'm aware is a dauntingly costly and very time-consuming process. And despite the state's commitment to treating runoff, I'm expecting that it will, in my lifetime, that very little, a large fraction of urban runoff will not be receiving treatment before I pass away. So there are other options that potentially could be implemented more quickly, and there's just a framework here showing some of the concepts involved with those. Nothing is fast, though, so just to make sure in case anyone catches quickly and thinks that means right away. Next slide, please. So the information that I presented is based on literature reviews that SFEI has conducted with funding from the San Francisco Bay Regional Monitoring Program and the California Ocean Protection Council. An overall framework addressing the particles themselves with some minor mention of the chemicals will be presented in a report that you can anticipate at the end of the summer that we're completing for the California Ocean Protection Council. Thank you for the opportunity to share this information. I'd be happy to take a few questions.
Thank you, Dr. Moran. Okay, so we'll now, next slide, please. We'll now be taking some questions regarding Dr. Moran's presentation. Once again, if you have a question, go ahead and click the Q&A button at the bottom or press *9 to raise your hand. You can also email saferconsumerproducts@dtsc.ca.gov. So first question says, where do you see bioretention fitting into the solutions pathway?
So there are two pieces to this. One is a science piece. So scientifically, research has shown that bioretention, which is a form of urban runoff treatment, is effective at removing at least one of the chemicals that has been linked to toxicity. That'll be a discussion tomorrow that DTSC will be having. Installing those systems is costly and not technically feasible in all locations. So there's a very strong public policy angle to this, as I mentioned.
Okay, thank you. Next question. Given that SFEI's research seems to suggest that TWP, at least those in fraction studies to date have measured, settle out of the water column, what can you say about how TWP and associated chemicals behave in oxic and anoxic environments, for example, in sediments?
I couldn't fully understand the question, which contained a number of abbreviations, and your voice wasn't very clear, but I think it was asking me to speculate on the fate in aquatic sediments of tire wear particles, and that's certainly beyond the scope of what I was able to present today.
Okay, well, it looks like that will be our last question before moving on. We do have one quick question from Sarah Amick.
Hi, Kelly. It was my understanding in the SFEI report that the report found black rubbery particles, but can you confirm what work SFEI has done to actually confirm that those particles are in fact from tires and not from another source that could also be made with synthetic polymers?
Two types of work. So the first is that confirmation samples were sent for further analysis, but only a subset of all the particles because of the cost associated with that. So that we know the black rubbery particles that were tested were consistent with those containing styrene butadiene rubber. Not all tire particles contain styrene butadiene rubber. And in fact, there's some issues with that have been recently published out of Australia. So, but that confirmation test did give confidence that that was indeed the source. And then the other source is that we have been pursuing for the Ocean Protection Council identification of sources of tire material into the environment and rubber particles. So we produced a conceptual model that just completed peer review, and that'll be published later this year. But basically, there are no other significant sources of this type of material in the California environment. There are other sources, so it's non-zero, but there are no other significant sources to urban runoff, which is the question I believe you're asking. Thank you.
Thank you, Dr. Moran. So this concludes our presentation and our Q&A session on San Francisco Estuary Institute. I would now like to invite Dr. Eric Van Genderen and Dr. Adam Ryan from the International Zinc Association to present. Next slide, please.
Great, thank you. I want to thank DTSC and the other panelists for the opportunity to contribute to this workshop. So we're going to be talking about the ecological risk assessment of motor vehicle tires containing zinc, which has been touched upon from several angles today. I want to start by recognizing that the International Zinc Association has been engaged in this process since about 2016. All the information described today has been previously provided to CASQA, to DTSC, and to the California State Water Boards, as well as other partners like USTMA. I am accompanied today in this presentation by my associate, Dr. Adam Ryan. Next slide, please. So we will address 5 fundamental issues regarding the risk assessment of motor vehicle tires containing zinc. Dr. Ryan will illustrate the consequences of using 35-year-old procedures and the current trajectory of science-based risk assessment. And I will start by describing the deficiencies of a petition and consequently a rationale that have ignored 21st century science. Next slide, please. So to begin, this is the distribution of relative zinc loading from tires reported in 6 different source apportionment studies around the world, and a number of these have been touched upon already. The study boundaries here range from individual cities, Auckland, New Zealand, Los Angeles, to entire watersheds. That's the Puget Sound study. Countries, so we have studies at the level of Germany and the Netherlands, which have been mentioned. And there's also an entire continental risk assessment, the European Union Risk Assessment Report for Zinc, which was published in 2018. One of these studies is not like the others. You can see that CASQA reported 74% of all zinc in the Los Angeles watershed was attributed to tires, which is in stark contrast to all other studies, which did not report a relative load greater than 6% plus or minus. Depending on the interpretation of the data provided, you've also seen USTMA suggest that those percentages can be up to 10%. The CASQA report did compare their results to a couple of these other studies, but was very deliberate in hiding the contradiction that we see here. Such inconsistencies do not support the claims made in the petition or the rationale concerning risks from motor vehicle tires containing zinc. Next slide, please. So, sorry, could you, so this is the science that supports a desktop risk assessment that we provided to DTSC. Of the 22 studies considered in our risk assessment, this 2012 review by Rhodes represented an untapped resource that was overlooked by all previous researchers. That is the actual release of zinc from tire wear particles. And so we generated a multivariate empirical model from this study. And our model included the pH of the water that was used in the exposure or the leaching procedure, the median diameter of the particles, and the loading of the particles in that sample. The model did not suggest the significance of the temperature of the water or the residence time was important or significant in the model development. In fact, zinc release from tire wear particles behaves no differently than what naturally occurs in the mineral phases found in soils and sediments. So this is a very similar type of analysis and type of model that we see in terms of the zinc being liberated from minerals that naturally exist in our environment. Now, please note that the microplastics report by SFEI and concerns about microplastics in the environment are absolutely valid. But zinc from these sources is not part of the problem. Next slide, please. So, as I suggested, we put together the only comprehensive risk assessment of tire wear particles and dissolved zinc along the entire exposure pathway. Basically, this is a reasonable worst case scenario. Following 90-day dry period, the average rainfall over a 100-year period in September falls on a 90th percentile vehicle frequency from a Caltrans database, which is then washed off into the roadside soils. And that then leads to the fresh water and eventually depositing into sediments. The fresh water here is also a reasonable worst case scenario. It's the 10th percentile river flow of all rivers in the Los Angeles area. And the water quality we're assessing is the 25th percentile of all bioavailability based constituents that are used for what people have described as the Boddick-Liggin model. So even a scenario that represents this reasonable worst case scenario would not pose a risk to ecological receptors. We see that the characterization of tire particles and zinc in this model matches no effect concentrations published in the literature for particles or zinc in any of these diverse ecological receptors. So as such, the Casco petition and the resulting DTS rationale is incomplete. And with that, I'll turn it over to Dr. Ryan, who will talk about specifically the situation in California.
Thank you. On the last slide, next slide, please. On the last slide, Dr. Van Genderen mentioned tire wear particles and dissolved zinc. Now, before zinc is bioavailable to aquatic life, it has to be in the dissolved phase. Zinc in particulate form, either bound tightly in the tire wear particle matrix or precipitated as inorganic minerals, is not bioavailable. So being dissolved is a prerequisite for bioavailability. And bioavailability was a concept that was described in the rationale document. This conceptual diagram shown on this slide describes the Boddick-Liggin model, or BLM, which is the state of the science bioavailability tool for zinc. In short, zinc bioavailability is linked directly to the concentration of free zinc ion, or Zn2+, which is affected by surface water chemistry, including dissolved organic matter, hardness cations, and pH. For example, zinc forms chemical complexes with organic and inorganic ligands, making zinc less bioavailable. California's current hardness-based water quality objectives represent only one of the three types of interactions that influence zinc bioavailability, namely the cations pathway. Next slide, please. To look at bioavailability in California, we conducted an analysis using surface water data from the Water Quality Portal. In our analysis, we compared water quality objective exceedances using the zinc BLM and also using the hardness equation. This figure shows a summary of the nearly 200 sampling locations represented in the data set. We see that only 2 sampling locations showed exceedances of water quality objectives if bioavailability is fully considered using the BLM, and those are represented here by orange data points. When this approach is applied, zinc exceedances are not widespread. And regardless of source, zinc does not represent a substantial and widespread concern. Next slide, please. Using the same data set, we looked at exceedances of California's obsolete hardness equation for zinc water quality objectives. In this case, 40 locations showed exceedances. And those are again represented by the orange data points. Next slide, please. This figure shows the results of the analysis on a sample-specific basis. Any point plotted above the horizontal dash line represents a water quality objective exceedance when the BLM is used. Any sample to the right of the vertical dashed line represents a hardness-based exceedance. Only 2 samples, those above that horizontal line, would be considered exceedances when the BLM is used. In contrast, there are 157 samples that exceeded the hardness-based water quality objective. And those exceedances came from the 40 locations shown on the previous slide. So when using the BLM, and I just also want to point out that there were 1,085 samples in this analysis. And when using the BLM, we saw a 0.2% exceedance rate, and that does not represent a widespread issue from all sources. And this highlights the need for using bioavailability models for zinc. Currently, we are also combing through over 1 million records from the CEDN database to add to and possibly refine our evaluation that's presented here. The next slide, click to the next slide, please. And click one more time, please. it shows a sampling of the scientific studies supporting the use of bioavailability-based approaches for zinc. And this last paper, enclosed in the red box, was the basis for our bioavailability calculations. Notice that this approach incorporates bioavailability using US EPA guidelines for deriving water quality criteria. And also notice that this paper was published in 2012, demonstrating that the science here is indeed mature. Next slide. Here we summarize some observations for further consideration. First, we know that zinc in tire wear particles itself is not bioavailable. Second, the importance of zinc bioavailability is recognized by many jurisdictions, many of which are replacing or have replaced their obsolete hardness-based water quality objectives. And again, the rationale document also recognized the importance of zinc bioavailability. And finally here, the DTSC rationale suggests zinc toxicity to purple sea urchins. However, the urchin barrens offer a real-world contradiction to that. For example, in the Bay Foundation's annual report in 2020, the effort describing the manual removal of purple sea urchins is staggering. There were more than 10,000 hours of dive time and more than 4.5 million purple sea urchins removed over a 7-year period. So the rationale for granting the zinc and motor vehicle tires petition is based on outdated water quality objectives and insufficient weight of evidence. Next slide, please. And here we revisit our opening slide. We've discussed that the water quality objective for zinc is outdated. Dr. Van Genderen described how the CASCA source apportionment report was inconsistent with other sources. The CASCA petition and subsequently DTSC's rationale for zinc and motor vehicle tires are incomplete. And we know that there is interest in bioavailability-based water quality objectives in California, which circles us back to number one, which is an important line of evidence for any potential adverse effects. And finally, I just want to say that we second Sarah's statement on slide 64, which was a comment about agencies working in a vacuum. And namely that, we recognize that if the Cal EPA departments operate in isolation, the stakeholder priorities won't be met. And with that, I think we're done. Next slide. That concludes it. Yep.
Thank you, Dr. Ryan and Dr. Van Genderen. We will now take some questions regarding IZA's presentation. So once again, go ahead and put in your questions in the Q&A at the bottom of the toolbar or press *9 to raise your hand. First question says, Eric, did you say that in your model, the water washes off the road into the soil and then into water bodies? My understanding is that the concern is when water washes directly off of roads into water bodies through stormwater pipes. Soil could change concentration and chemical properties.
Yeah, that is correct in terms of the way that the model we built was parameterized. However, we do know that stormwater conveyance systems oftentimes have sediment that collects in them as well. And whether it's soil or roadway particles, sand, silt, all of these are basically cationic exchange surfaces that can bind metals, zinc, copper, and the like. And so while a roadside soil may not accurately reflect what's happening in the conveyance system, there are similarities in terms of what affects bioavailability and transport.
Thank you. Okay, so next question says, do you have a unified saltwater BLM or are you developing one? Has one been developed based on toxicity to broadcast spawners?
We have looked at developing a saltwater biotic ligand model following the approach that the copper that EPA has recognized in a draft copper update. For zinc and copper, it's organic matter, dissolved organic carbon that is the most important factor. affecting bioavailability, since salinity and pH are not as broad ranging as they are in freshwater, or as the constituents change in freshwater. Those studies that we've conducted relative to the influence of dissolved organic carbon on zinc toxicity in salt water are for urchin and mussels.
Okay, I'm going to give a couple moments for some questions to come in. It says, does zinc risk assessment exposure characterization also account for first flush events? Or does it pertain primarily to chronic conditions of California surface waters?
I guess the answer is both. We have unified zinc bioavailability models for both acute and chronic criteria scenarios. So we've conducted analyses on both of those.
Okay. So it looks like that is all we have time for right now. This concludes our Q&A session on IZA's presentation. I would now like to invite Ken Schiff from the Southern California Coastal Water Research Project to present.
Good morning, everybody. If you could advance to my first slide, I'd be grateful. My name's Ken, and I'm from the Southern California Coastal Water Research Project, more commonly known as SCWRP. It's important to know that we're a public research agency. We don't have any role in the regulatory process. We have no involvement in the petition, and we certainly have no role in advocacy. If you want to find out more about our agency, including downloading copies of the study I'll talk about today, or any of our other research projects, I invite you to go to our website here listed on the front page. If we could go to the next slide, please. Before I provide any details, I want to give a little backdrop on this study, which was conducted over 20 years ago. It was a long time ago. And it was at a time when the first municipal stormwater discharge permits were being issued. And nobody really knew much or anything about effects of stormwater on the environment, and especially in the ocean. Here's a citation for the article that I'll talk about today. Let's go to the next slide. The study had many questions. Here's three that are relevant to our discussion today. The first question is whether stormwater discharges from Ballona Creek, which is a very urbanized creek in Los Angeles, was toxic to marine organisms. The second question is whether the extent and magnitude of this toxicity to marine organisms was occurring offshore of the creek mouth in Santa Monica Bay during storm events. And then the third article, assuming it was toxic and it was a large extent and a high magnitude, what were the toxicants that were responsible for this? So 3 study questions. Let's go to the next slide. So before I go any further, I want to let you know that we are defining toxicity to marine organisms in this study as toxicity to sea urchin fertilization and can they reproduce well. So obviously this is a species that lives in California. The test itself is reasonably short, which makes it a good analog for stormwater exposures. They definitely occur within the time frame of storm events. It looks at the success of fertilization and start creating embryos so they can reproduce. And it is an EPA and California approved method. Let's go to the next slide. So before I give you any details, I'm just going to give you the answers to the 3 questions. And then I'll kind of follow on each of these answers with a little bit of data and give you an example of how we reached that conclusion. So the first question is whether the Ballona Creek stormwater discharges were toxic, and the answer is yes. And this is toxic from the pollutants in the runoff, not from the salinity. We would adjust every sample to the salinity of seawater. So it was really from the pollutants, not just saltwater or fresh water on saltwater organisms. It was reasonably extensive in the sense that we could measure toxicity up to a mile offshore and maybe twice that distance alongshore in Santa Monica Bay near Ballona Creek. And then the last one is that based on our results, the toxicity was generated by trace metals, most likely zinc. So let's look at a little data. Next slide, please. So here's an example of the data. This is from 2 different storms. That represents each of the plots on this graph for 2 storms about a month apart. And the y-axis on this graphic represents the percent of normal fertilized sea urchins. So relative to a non-toxic control. And so basically a higher number is better. If it's 100%, you're doing great. The lower the number, the more toxicity there is. The x-axis represents the percent of stormwater in the sample. That's based on salinity. So, so 100% stormwater is, fresh water, and 0% stormwater is all saltwater. And so the way you interpret these graphics is as we got more and more stormwater in the sample, it became more and more toxic. The dashed line represents the sample we collected out of the creek. And so you see we're seeing effects at fairly low percents of stormwater. The filled circles were samples that we had collected offshore in Santa Monica Bay. And you can see that the patterns of dose response in these 2 samples fit pretty closely between the creek and in the offshore area. Let's go to the next slide. The second question is what the extent and magnitude of toxicity offshore in Santa Monica Bay was during storms. And the answer I gave you was that it was reasonably extensive. And so this is a map of Ballona Creek, which is that very straight channel that's coming across the land, shown here in gray. Marina del Rey discharges directly adjacent to it. And the contours represent the percent fertilization success in our sea urchin tests. The contours were based on salinity, relationships between toxicity and salinity. And the actual mapping was done via ships offshore during the storm event. So 80% fertilization, which is the outermost contour, generally represents the level at which significant toxicity occurs. And so this is why I give this conclusion that it's fairly extensive. So you can see the highest concentrations of toxicity or the highest levels of toxicity were immediately in front of the Ballona Creek mouth and the Marina del Rey mouth. And what kind of concluded to us that this was a true conclusion is while we were out on the ships, we would take samples, individual grab samples for toxicity, and they matched these contours pretty well. So a validation. Let's go to the next slide. The third question is, what was the potential toxicant that might have this extent and magnitude of toxicity? And for that, we use a toxicity identification evaluation, or a TIE. It's a forensic tool for trying to identify what the contaminants are. It's an approved EPA and California method. It's been around, well, for at least 20 years. And the way it works is you treat your original sample with different mechanisms to remove toxicity. So in this particular example on the top graphic, we had taken a sample of Ballona Creek stormwater. And on the y-axis is the percent fertilization. So higher numbers are better than lower numbers. The dashed line represents the original toxicity in the sample. And then you can see along the x-axis, we removed different parts or potential sources of toxicity in the sample, like removing particles, removing organic contaminants like pesticides, and then removing trace metals. And so you can see when we remove particles in that top graph, or we removed organic contaminants in that top graph, the amount of toxicity from what we originally measured didn't change. But as soon as we removed the trace metals, we removed all of the toxicity. So that was our first indication that trace metals might be something to be concerned about. Intriguingly, we did the same process on one of the samples of surface water offshore Ballona Creek in Santa Monica Bay, and we saw somewhat similar results, that removing trace metals removed the majority of the toxicity. I'll also point out that removing some other things also removed a little bit of toxicity, which is a little different than the creek. So potentially there were other contaminants offshore in Santa Monica Bay as well. Let's go to the next slide, because this was the TIE, toxicity identification evaluation, shows that trace metals, but it doesn't say which trace metal. And so what we did was start comparing concentrations that are typically measured in stormwater from the County of Los Angeles during their routine monitoring of the discharge, and compared that to toxic levels, known toxic levels in sea urchins. So in this particular instance, I'm showing you the no effect concentrations. That's essentially where no toxicity is expected. And then the effects concentration at 50%, sometimes called the EC50. That's where 50% of the population, or 50% of the, in this case, sea urchin, won't get fertilized. So kind of a no effect level and a median effect level. And I compare that to the concentrations we see in stormwater. And for 5 of these 7 trace metals, the concentrations we see in stormwater are well below, orders of magnitude below any kind of effect level we might see. Copper looks like it's starting to approach a potentially toxic level. So copper could have been one of the contaminants that was contributing to toxicity. But when you look at the concentrations of dissolved zinc in stormwater relative to the levels of dissolved zinc that might start putting effects even at the 50% level for sea urchins, then much greater. And this is what kind of got us to reach this conclusion that zinc was a likely contaminant. Let's move to what'll be my last slide, please. So to finish out the presentation, we actually repeated this study down in San Diego Bay, offshore of another very urbanized watershed, Chollas Creek. And intriguingly, the answers were very comparable to what we'd seen in Santa Monica Bay, including extent and magnitude. And when we conducted these toxicity identification evaluations, and this time with even greater rigor as well as confirmation, zinc once again turned out to be the contaminant of greatest concern. My last bullet gives you the citation for that if you'd like to look into it a little further. And this concludes my short presentation. Thank you.
Thank you, Mr. Schiff. Next slide, please. Okay, so we'll now take some questions regarding Mr. Schiff's presentation. Again, you can go ahead and email *9 or click on the Q&A at the bottom of your screen. I'll give a few moments for questions to come in. Okay, first question says, have annual stormwater plumes changed in frequency or magnitude since this work was done?
So clearly stormwater plumes are a function of how much rainfall occurs. And so, the bigger the storm, the bigger the plume. To my knowledge, they haven't changed very much. We've done quite a bit more work on measuring plumes since then. I'll be glad to forward that if the questioner would like. But I think your question is whether the toxicity of the plume has changed over time, not just the plume itself. And that, I can tell you, I haven't seen a lot of more of that work done in Southern California.
Okay, there's a follow-up question. It says, how do you think stormwater plumes along the California coast will change as climate changes, and will they be more or less severe?
Well, that's an excellent question. Asking me to predict what climate change is going to do, which of course I can't. What I can tell you is what the current climate change models are saying based on other researchers in the region, which is that we will, in our particular region, we may get punctuated with very large storms, which would then increase the size of a potential plume. What the size of the toxic portion of that plume would be, I can't tell you.
Thank you, Mr. Schiff. So it doesn't look like we have any other questions at this point. So I'm going to go ahead and move on to our next presenter is Dr. Ali Ansarifar from the Loughborough University. Dr. Ansarifar, if you could, next slide, please.
Yes, can you hear me?
Yes.
Very good. Let me see if I can get the video going now. Okay. Thank you very much indeed. Please accept my apologies for causing confusion at the start of this meeting. I had a bit of problem to connect. Well, I'm Ali Ansarifar. I'm based in the UK. I've been working at Loughborough University in the materials department, and I've recently retired. I'm still supervising a PhD student, and the results which I'll be presenting to you is from her work. My other colleagues in the chemistry departments are Ms. Dr. Weaver and Professor Vijayanta, who have been helping me with my project. First, I'm going to give you a bit of background to what we consider to be a major problem with the Q system in tires. Can we go to the second slide, please? Yes, this is a Q system from a typical tire formulation. This is NR, natural rubber-based tire belt skim compound. We selected this compound some years ago from a rubber formulary book, which had a set of a range of compound formulation. And what you see in this table is the Q system only. I have not included the remaining ingredients. So what you have here basically is a zinc oxide, which is considered to be as a primary activator. You have stearic acid, you have, which is a secondary activator. You have hexamethylmelamine, which is a primary accelerator. And you also have dicyclohexyl 2-benzothiazole sulfonamide, which is a secondary accelerator. And you also have sulfur, which adds up to 5 parts. So if you add all these chemicals together, that's 15.7 parts per 100 rubber by weight, and 10.7 parts of it is curative. So that is quite a lot of chemicals to use to cure a rubber. And in most of the Q systems which we examine, the zinc oxide was sometime around 5 parts. It had the highest loading, and then you had the the accelerators and the curing system, etc. So what we decided to do is to see if we could reduce the use of zinc oxide, and at the same time, we could reduce the use of other chemicals with it, because zinc oxide having the highest loading among the Q system was of concern. And the question, of course, is if we could make the use of zinc oxide more effective, how will it affect the remaining chemicals in the Q system? And if you look at this number of chemicals which go into the rubber, they of course have to be mixed. Ideally, when you want to use so many chemicals, you like them to be together so they can react together to produce very efficient Q system. But the problem is when you disperse so many chemicals inside the rubber, there is no guarantee that they are going to come together to react at the same time to produce crosslinks in the rubber. And this is why we believe the problem of unreacted chemicals can cause migration and leaching of zinc oxide and other chemicals into the environment. So the question is, how do we deal with this? Can I have the third slide, please? Now, the solution we are offering is this, that we want to reduce zinc oxide usage in tire. The way we do it is to combine zinc oxide with a sulfur-bearing accelerator into a single additive component. So what we are doing, basically, we are bringing together three components, very important components in the sulfur Q system: zinc oxide, which is an activator, an accelerator, and of course, if the accelerator has sulfur in it, you have the accelerator, sulfur, and zinc oxide as a single product. And the way we achieve this is to coat zinc oxide with the accelerator to produce a single powder. Next slide, please. Now, the materials we use were standard Malaysian rubber natural, which is 98% 1.6 content with a molar viscosity of 89 units. And the chemicals we used was tetramethylthioron disulfide, known as TMTD, which is a sulfur donor accelerator, and zinc oxide as activator. You notice that we did not use secondary accelerator, which is esteric acid, often used with the zinc oxide in most sulfur Q system. So we have taken that out. We didn't use secondary accelerators either. So by this method, we are hoping to eliminate excessive use of these accelerators and activators. And at the same time, we are hoping to reduce the level of zinc oxide, which we use in the sulfur vulcanization of rubber. Next slide, please. Now, zinc oxide was treated with different amounts of TMTD, from 35 milligram of TMTD per 1 gram of zinc oxide to 400 milligram of TMTD per 1 gram of zinc oxide in an organic solvent to produce a single powder. So basically what we did, we took the zinc oxide and we started to apply different amounts of TMTD on the surface of zinc oxide to produce a range of powders. We put these powders individually into natural rubber and we cure it at 160 degrees centigrade to see which powder produces a reasonable Q. And when we examine our results, we noticed that the powder with 400 milligram of TMTD per 1 gram of zinc oxide gave a very good Q. So we had the powder now, we had the combination of TMTD and zinc oxide. The powder which was selected and used in a subsequent work had this combination of 400 milligram to 1 gram of zinc oxide. That is roughly 28% of the powder was TMTD and the rest of it was zinc oxide. Now, if you take, for example, 1.48 PHR of the powder, the TMTD to zinc oxide ratio would be 0.42 PHR to 1.06 PHR. Now, if you use a higher level of the powder, for example, 12 parts, then the ratio of TMTD to zinc oxide goes to 3.43 to 8.57. And if you go to 20 parts of the powder, the ratio of TMTD to zinc oxide is 5.72 per 14.28 parts. So the ratio of TMTD to zinc oxide depends very much on how much of this powder we use. And in a subsequent work we did with polybutadiene and ethylene propylene diene rubber, the very maximum amount of powder we used was 3.5 parts. And that would give you a ratio of 1 part of TMTD to 2.5 parts of zinc oxide. So 2.5 parts of zinc oxide was the maximum zinc oxide loading which we use in our subsequent work. And that means the normal loading of zinc oxide, which is 5 parts in typical sulfur-Q system, we managed to reduce that to 2.5 parts. So we achieve a 50% reduction in the use of zinc oxide. And at the same time, we also eliminated the use of secondary accelerator and secondary activator. You also notice that we didn't even use sulfur powder in order to cure the rubber. So we have achieved quite a substantial reduction in the use of this chemical. Can I have the next slide, please? No, the question is, when you reduce the number of chemicals to 1 from 5, will it cure the rubber? Well, here is a typical Q trace. On the vertical axis, you have the load, the torque. On the horizontal axis, you have the time. As you can see, the rubber cures very well. At the bottom, you have the minimum torque. And when the rubber trace plateaus around 30, that gives you full Q. The difference between the minimum and maximum torque on this trace is called delta torque. Delta torque is an indication of cross-link density changes in the rubber. So if the delta torque is low, that means the rubber is not cured properly. But if you get a good number for delta torque, that means the rubber is cured. And according to this trace, our rubber is cured perfectly well, even if we use 1 single additive in our cure system. Next slide, please. Now, this is delta torque on the vertical axis versus the TMTT loading in the powder. So what we are doing, we are looking at see what happens if the amount of TMTD on the zinc on the surface of the zinc oxide increases. How will it affect the delta torque or the cross-link density in the rubber? As you can see, we start from 1 part TMTD loading in the powder. It increases the torque increases to around 22, 23. And if you increase the loading of TMTD in the powder to 3.5, you get a less improve in the value of the delta torque. And in this line, as you can see, the line breaks at about 1.57 PHR. So by this method, which uses the Q traces from the isoelectric disc rheometer at 160 degrees centigrade, we have managed to measure the exact amount of the powder which is needed to cure natural rubber. And this gives us 1.75 of TMTT needed on the surface of the zinc oxide to give us a full cure. And this method has been used to measure this amount of TMTT for polybutadiene rubber and for ethylene propylene diene rubber. So this works always well, and it gives us the optimum loading. Basically, that means you don't use less, you don't have to use more. You can use exactly the amount which a figure of this nature will give you. Number 8, please. No, this is a scorch and optimum cure time versus TMTT loading in the powder. Now, if you look at the top data, you notice that the optimum cure time of the compound is around 14 minutes. It increases slightly as the loading of the powder goes to 3.2. And when you increase the loading of TMTT in the powder, that increases further to about 17, 18 minutes. So according to this data, the less TMTT powder you put in the powder, the more efficient is the cure, because you get a much faster optimum cure time. We can cure the rubber at a shorter time. Similarly, if you look at the scorch time, because the red data, at about 1.1 PHR TMTD in the powder, you have got a 2-3 minutes scorch time. And as you increase the loading of TMTD in the powder, the scorch time doesn't change that much. So basically what this means, if you use the least amount of TMTD in the powder, you can get the shortest scorch time. So traditionally, people think the more chemical you add to the rubber, the more efficient that becomes, the more efficient the cure becomes. But from this data, it is the other way around. The less chemical you put in the rubber, the more efficient is the cure. The sooner the rubber cures and the sooner it starts to scorch. So as you can see, the amount of the TMTD in the powder is very modest, but we can get very perfect cure for the rubber. Slide 9, please. Now, the cure rate index is always a measure of the rate of...
Excuse me, doctor?
Yeah?
I know that you're very close to the end, but for the interest of time, I really apologize. Can we advance to your conclusion slide?
Yeah, of course. Yeah, very good.
Thank you.
Nine, 10? Can we go to 10? Yeah, very good. My conclusions, summary, what we like to propose is to use zinc oxide in tires. We like to combine zinc oxide with a sulfur-bearing accelerator to produce one single component, which we call a powder, to vulcanize the rubber. What is good about this, that it reduces the number of additives from 5 to 1. But if I want to take this work further, I would like to use a more efficient sulfur donor accelerators. TMTD is classified as carcinogenic. It's a bit of a problem at the moment. But if you can have a safer accelerator, which can release more sulfur, and it could be coated on the surface of zinc oxide, that will be a very ideal compound, ideal additive to use in order to cure the rubber. So this is the message I'd like to leave behind, that every chemical we can reduce everything, 5 chemicals to only 1, and use it efficiently without compromising the cure of this rubber. Thank you very much for your attention.
Thank you, Dr. Ansarifar. It looks like our first question is, have tire manufacturers experimented with strategies like that you described, or is the research still wholly academic?
No, at the moment, I'm afraid it is academic, but my results have been published extensively in Tire Technology International. So I put that in the public domain. And also I presented my results in the Tire Expos conference in Germany. So they have had a lot of exposure to this technology, to my ideas. And I'm very much hoping that one day they take this technology and test it in the tires. I haven't seen anything yet, but one of the reasons that I was very happy to join your conference, because I know that this problem is not is receiving a lot of attention, and hopefully something will be done to reduce these chemicals, particularly zinc oxide. And I'm hoping that my work will eventually contribute somehow to the advancement of this work.
Okay, so we, in the interest of time, we have one more question. It says, concerns with the nitrosamines from TMTD?
Yes, I'm afraid that's the problem. I've been told a number of times when I presented my results, I said I use TMTD, and I've been told it's carcinogenic and it's not safe anymore. So I'm hoping, if I was to take my work further, I would look for a much safer accelerator, which has a bit more sulfur in it. TMTD has 13% by weight sulfur. Ideally, I like to see a safer accelerator, which is not carcinogenic. It can replace TMTD, and it has up to 15, 16 to 17% sulfur. If I had that that type of accelerator, then I believe I can take this to a higher level and present it to tire manufacturers as a possible option for the cure system.
Okay, thank you, Dr. Ansarifar. So it looks like that will be the conclusion to Dr. Ansarifar's presentation, and we'll now move on to the public comment. If you can go to the next slide, please. Oh, one more.
Yeah.
And one more. And one more. All right, perfect. Okay. So I'll now read through the public comments. So go ahead and use the same procedure that you've been using. So click on the Q&A button, press *9 from the phone to raise your hand, or you can email us at the Safer Consumer Products. So right now the public comment says, the presentation misconstrues my comment on the Los Angeles Zinc TMDL. Concern was that the relatively short-term TMDL deadlines would not allow DTSC product review process to have an impact on the presence of tire-related zinc in runoff. And this is from Fred Krieger. I'll give a couple more moments for anyone else that would like to have a public comment. Okay, it looks like we have a comment from Sarah Amick. Go ahead.
Can the previous speaker, Ali, comment on the scorch safety for compounds with TMTD accelerator?
Yes, there are very scorchy compound we found. They start to scorch very quickly, and the rate of cure is also quite impressive. So basically, short time scorch compound. It depends how you formulate it. For example, if I use some of this compound in SBR BR blend, for example, the scorch is very short. You get a very rapid scorch. But in other compounds, for example, polybutadiene on its own, then I noticed that the scorch starts to change. So really, it depends on the formulation. It depends on the compound you use. I cannot say for sure a single rule which you can take away from me.
Thank you, Dr. Ansarfar.
Yeah.
So we're going to go ahead and allow another moment just to receive any public comments at this time. We're going to go ahead and take more questions after this public comment period. So right now we're just taking public comments. Give you another moment if anyone has any. Okay, looks like we have Howard Colvin. You can go ahead and unmute yourself.
Yes. Hold on just a moment here. Can you hear me?
Yes.
Yes. The two questions. One is the scorch time, which Sarah alluded to. Can you give us numbers compared to, say, a sulfonamide cure, which is used in the industry? Are we talking 3 times the less scorch, 4 times less scorch, or do you have any thoughts on that?
With the powder which I used in natural rubber and polybutadiene and EPDM, the scorch time varied depending on how much compound depending on how much additive I used, and depending on the composition of the rubber. So all I can say, if you hold on, please. If I said to you, a scorch time, yeah. In the case of a scorch time, is 1 minute, 1.1 minute for the natural rubber with the powder we used. So it is a very short scorch time.
Yes,
that is at 1.1 parts of TMTD in the powder.
Yes. And as you know, the scorch time in the tire industry is very important for processing.
Of course.
Have you done any cross-link type and density work compared to, say, conventional sulfonamide cure?
Not yet. So far, we have relied on the delta torque as a means to guide us. But really, at the moment, my PhD student is doing a lot of solvent swell tests on a range of samples made of natural rubber, polybutadiene rubber, and EPDM to see how we can identify different type of crossings which will form using this single powder. So we are really at the earliest stages of work with respect to that kind of idea you just mentioned.
Okay, thank you for that. We've got a couple of people with their hands raised. So William Walsh, if you can go ahead and unmute yourself and make your comment. Mr. Walsh. Okay, I'm going to move on to the next one. Greg Bowman, if you can unmute yourself and go ahead and make your comments.
Yes, this is kind of a follow-up to Howard Coven's question. I guess the question is, cross-link type is extremely important with regards to performance of the compound and various components. Since you did not do any cross-link type testing, did you do any fatigue testing? You demonstrate good fatigue in the components.
Yes, good question. At the moment, not yet. I haven't done any mechanical testing, fatigue measurements on the rubber. But most of the work we have done so far has been concentrated on basically getting this powder right, understanding how it performs in the rubber, how it performs, affects scorch and optimum cure time, the rate of cure and all that. So it is really at this stage a bit of preliminary work, but we are moving into finding out the crossing, the type, and eventually the mechanical properties of the rubber itself.
Okay, thank you. I'm going to ask William Walsh one more time. If you could go ahead and unmute yourself and make your comments. Okay, so at this time, we're going to go ahead and move on to our questions section since there's no more public comments. So I'm going to go ahead and start reading some of these questions. Okay, it says, in the last presentation, the zinc oxide levels are very high and representative to current levels used in compounds. Can you respond to this fact? Okay.
Hello? Yeah. Is it me?
It's okay. I'm going to move on to the next question. So it says, are you seeking supplemental information related to the aquatic organisms only, or are you seeking information related to impacts in California? I believe this is a question for DTSC.
Yeah, thanks, Jessica. I'm Ann Cooper-Doherty with DTSC, and I think at this point we've been focusing on the aquatic impacts based on the findings from the petition. But if anyone's got information on other impacts, we certainly welcome that information as well.
Thank you. So I have another question here that says, do you have an estimate of when the US EPA will develop a BLM or multiple linear regression-based recommended water quality criteria for zinc?
Hi, this is Adam here. I will address that one. US EPA, through the Cooperative Research and Development Agreement with the Metals Associations, is looking to have bioavailability models finalized in 2024.
Okay. So next question. Looks like William, your hand is raised again. If you can go ahead and try to unmute yourself and ask your question. Okay. So it doesn't look like you can get the muting to work. And unfortunately, due to time, we're unable to answer all of the questions. Since we did receive a large number, we apologize. But again, this will be our last, that was our last question. So this concludes our Q&A session, as well as our presentation for today. Thank you for your interest in participating, especially during this unprecedented time. I will now pass it off to Andre Algazi, Chief of Chemical and Product Evaluation Unit within the Safer Consumer Products Program, for closing comments. Andre?
Thank you, Jessica. So as Jessica indicated, I lead DTSC's Chemical and Product Evaluation Team, which evaluates products in our work plan to identify potential priority products. And today we're talking about tires. I want to thank all of our speakers today for sharing their diverse perspectives about zinc in tires today. You've given us a lot to think about as we consider our next steps on the proposal. And many of you have been engaging with us during our evaluation of the petition, and we're counting on your ongoing engagement as we move forward. And I also want to acknowledge our staff for their work on evaluating the petition, as well as developing our rationale document, which is posted on our CalSafer portal, and for planning today's workshop. Our comment period closes on Friday, August 6th. So you have another 10 days to submit comments on our proposal to regulate motor vehicle tires containing zinc as a priority product. We welcome all perspectives and data that can help us identify our next steps. In addition to information and data on the potential for zinc exposure from tires and potential adverse impacts resulting from such exposure, we're especially interested in information that would help inform our definition of motor vehicle tires that we've come up with as a proposal, and on any technologies that could reduce or eliminate the use of zinc in tires, or mitigate the leaching of zinc from tire wear particles, or mitigate the release of tire wear particles to the environment. Public engagement and comments are really a key part of our process. And so we're really counting on your participation. So please, if you haven't taken the opportunity already, submit your comments to us by next Friday. Once the comment period closes, our next steps will be to consider the information and data we've received during the comment period and finalize the rationale document, which we currently project to happen towards the end of this year, 2021, or early in 2022. So I just want to reiterate my thanks again to all of you for participating in our workshop on zinc in tires, and we hope we'll see a lot of you at this afternoon's workshop on other chemicals in tires, as well as tomorrow's discussion of 6-PPD in tires. So thanks very much, and have a good break. We'll hope to see you at 1:30 Pacific time.